Welcome to this lesson about the reinforcement learning with prior data or RLPD algorithm. RLPD is an advanced reinforcement learning algorithm based on soft actor critique. And this slide shows you all the additions that RLPD provides over SAC. So soft actor critique, you have two critiques and you take the mean over these two critiques to fight something which is called overestimation bias. And you have an actor that uses a squashed Gaussian distribution as output to a policy. If you need to know more about soft actor critique, see my video about it. And now let's have a look at the different additions that we will visit during this lesson. First, RLPD combines offline data corresponding to expert demos or more play data with online data coming from the interaction of the agent with the environment through a simple scheme which is called symmetric sampling. Second, it uses layer normalization, which is something now standard in advanced reinforcement learning. It combines it with using high update to data ratio or UTD ratio. And depending on the environment, so the things in brown, it uses one or two critiques to counteract or not overestimation bias, and it uses entropy maximization or not to favor exploration. So now let's have a look at those mechanisms in more details. First, balance sampling. So here is the scheme. This is inspired from an old paper from Ross and Magnell. And so the idea is that at each time step, you will sample a mini batch with half of the mini batch coming from offline data and half of the mini batch coming from online data. And the authors show you, as I will show in the next slides, that this scheme outperforms offline pre-training than online fine-tuning. But I have to say that this literature is evolving fast, and for instance, these results are contradicted by the Warmstadt reinforcement learning paper that I may cover sometime. So let's have a look at the results about the symmetric sampling scheme. First, with this figure, the authors show that using 50%, 50% or 25%, 75% mixing from both sources of data is equivalent. Okay, there is low sensitivity to the amount of offline versus online data to the algorithm. The only things that do not work is using 0% offline or 100% offline, which correspond to the green or blue curves. Besides, they show that another option would be to initialize the whole buffer with the offline dataset and then add online data. They call this seeding the replay buffer, and they show with this figure that using the online mixing that they use is better than the seeding process. Now let's have a look at the second mechanism, which is layer normalization. This is something that is now well accepted in the reinforcement learning community, that adding layer normalization improves reinforcement learning algorithms. In more details, the authors show that just using offline data and off-policy learning from a replay buffer is not enough to get strong performance. Using layer normalization is necessary in this context, and I will explain why later. But first, let's have a look at the results. So here you have the Q values, either using layer norm or not using it. Here also this is Q values, and you can see that if you don't use layer norm, you tend to have a strong overestimation bias. And this is also visible in the performance of the policy, which performs much better when you use layer norm than when you don't. And the authors explain why layer norm works. They take a simple batch of data and they measure the capability of a two-layer multi-layer perceptron to extrapolate beyond this data, and you can see that without layer normalization, if you ask the output of the neuron out of distribution with respect to the data, it will tend to overestimate the values, whereas if you use layer norm, it tends to prevent catastrophic overestimation. Preventing catastrophic overestimation is also a very active field in reinforcement learning. See, for instance, the implicit Q-learning paper from Kostrikov and co-authors. But the way they do so in reinforcement learning from prior data is simpler, just using this layer normalization. And now if we have a look at performance using layer norm, you can see that in some environments using layer norm is not crucial, but in others using layer norm provides a much better performance. The third mechanism consists in using high update to data ratio. So what's this and how does it work? The general idea is that the UTD ratio is the number of gradient steps that you take for each sample in the replay buffer. So for instance, if you perform 200 gradient steps for a mini batch of size 100, then your UTD ratio is 2. And the more gradient steps you make, the faster you will learn for the same quantity of data. But the problem is that high UTD ratio has been shown to result in statistical overfitting in that particular paper. So to prevent this statistical overfitting, there are different techniques. One consists in just regularizing the parameters of the neural network to prevent large weights so that you avoid overfitting. A well-known technique is also dropout, so where you mask the activation of different neurons. And the third one is random ensemble distillation, where you have several Q networks and you will average the gradients over this Q network to update your actor. And you train those different critics, not all at the same time, but for instance, you sample 2 of them and you update them over a set of 10. So in the RLPD paper, they take a set of 10 critic networks. Actually, they don't study if it would work better to use 12 or 15 or 5, but 10 looks good. And the idea is that they will update the actor taking the average over the critic gradients. And again, experimentally, they show that when they use UTD ratio of 10 instead of 1, their algorithm learns faster, so you are more sample efficient. That's the red against the blue and the dotted pink against the dotted black. The next mechanism is just to fight overestimation bias. So it is now common. It started with TD3 from Scott Fujimoto and colleagues. It is now common to use 2 critics and to take the mean of these 2 critics to prevent overestimation bias that you would get if you were using just 1 critic. But the authors of RLPD show that in some environments, using these 2 critics makes the process too pessimistic, and depending on your environment, you should use it or not. So this is what they do. They try with and without, and they pick the best depending on the environment. And to combine using these 2 critics, when they use 2 with ensembling that we have seen just before, what they do is that they choose 1 or 2 critics among the 10 critics to perform the updates and to measure the Q value of the action of the policy in the current state. Finally, the last mechanism is entropy maximization. So here the idea is that in algorithms such as soft actor critique, you generally try to maximize the entropy of the policy so as to keep the policy exploring as much as possible. So in practice, it means that you want the variance of this output Gaussian to be as large as possible. In soft actor critique, actually, you also maximize entropy within the critique to have something which is more consistent. And again, the authors of the RLPD paper show that depending on the environment, it's a good idea or not to use entropy maximization. Actually, you can find in several papers that sometimes soft actor critique, which uses entropy maximization, outperforms TD3, and sometimes it's not the case, and TD3 can be seen as a deterministic version of soft actor critique where there is no entropy maximization. So you can see that depending on the environment, entropy maximization can be good or can be bad. So again, they make the decision of using entropy maximization or not an environment dependent decision where they just try with and without and they pick the best. So overall, when you take these 5 mechanisms, this is described with this algorithm which is present in the paper and which is quite clear. If you just read the algorithm and you try to implement that, you will figure out how to code RLPD quite easily. And now let's have a look at the empirical results that they get. So first, I didn't say this before, but they evaluate their algorithm in 3 different environments. The first one is adroit, so it's a virtual hand manipulating things in 3 dimensions. You have the ant maze domain where a small ant with 4 legs has to move from one position to another one in a maze can be small, medium or large. And it can be also locomotion where, for instance, here you have the walker, here you have Alchita, and here you have the humanoid. And the idea is that in all these 3 environments, there are some pre-existing datasets that you can use in the offline part of the algorithm. And these datasets exist with different level of quality of the data, meaning some are expert datasets and some are just play datasets. So the front figure of the paper is this one. They show that using RLPD with the 5 mechanisms that I have told you about, you get much more sample efficient than using implicit Q-learning or soft actor critique. When you separate these results in terms of the different domains, you get exactly the same picture. This is only in the locomotion case that it's hard to beat the previous state of the art, so they are not better than the previous state of the art. And in Adroit and Antmaze, the prior state of the art is implicit Q-learning plus some fine-tuning, whereas in locomotion, this is off to on, which means off policy to on policy. But this one is hard to beat because it's already close to optimal. They provide a few ablations. So first, they look at how the algorithm behaves depending on how many layers you use in the actor or in the critique, with or without entropy maximization, with or without taking the mean from 2 critiques, and with or without random ensemble distillation, and they show that in any case the full RLPD algorithm is better than all these ablations. And again, the different figures correspond to the hardest environments into the different domains. So relocate sparse is the hardest Adroit task, Antmaze large diverse is the hardest Antmaze task, and humanoid walk expert is difficult, as humanoid is the most difficult locomotion task. They also show that you can train RLPD from images. To do this, they use a 6-layer convolutional neural network as input architecture, and people from the LeRobot repository told me that they can also use a pre-trained ResNet with 10 layers, and to make these things work they need to avoid overfitting, so they use image augmentation with random shift with 4 pixels, as this has been popularized by this paper about data augmentation. This paper is quite famous. The title is Image Augmentation is All You Need. The paper also provides all the hyperparameters of the algorithm that looks clean, and according to people in LeRobot who re-implemented the algorithm, everything is clearly specified, so that's okay. That's a paper that you can trust. And again, according to LeRobot members, there are a few additional details to be known. These different things matter a lot, so I did not specify this, but you need to normalize the reward, the state, and the action if you want to use RLPD in robotics domains. On robot, you should also initialize the policy very close to 0 by dividing the last layer weights by something like 100, so that you don't get a shaky behavior in the beginning of training, and this looks important in practice. And also something that is very important is that when you train these algorithms on a robot, you should decouple data collection from training, which means that you need 2 threads, one to collect the data and one to train the policy, and you will adjust the rate at which the actor is updated by the training thread depending on the computational capabilities of your architectures. And finally, people in LeRobot told me that RLPD is rather insensitive to the size of the replay buffer. And that's it for this lesson. Thank you for listening.